Okay, let's look at an example here. I had to put a little insert here because I left a word out. An insurance company found that over a 5-year period, 23% of those that received a speeding ticket one year received a speeding ticket the next year. So if you look down here in the transition matrix, A is those people that received speeding tickets, and I broke it up into 23% that received a speeding ticket the next year, and A prime would be those that didn't receive a speeding ticket the next year. So that's just 1 minus 0.23. It also says that they found that 11% that did not receive a speeding ticket that year received one the next year. So out of those, this row represents those that did not receive a ticket the first year. So 11% of those that did not receive a ticket the first year received one the next year, and then 89%, subtract 11% from 100, you get 89% that did not receive a speeding ticket did not receive one the next year. Here's the transition diagram, and so this circle represents those that received a speeding ticket, and notice that 23% repeated, which means 77% went to the other state where they did not get a ticket. And of those that did not get a ticket the first year, 11% went to the state where they did get a ticket, and 89% returned to the state where they did not get a ticket. Now, if we calculate S naught, so first of all we have to read B. It says if 5% received a speeding ticket this year, what is the probability that a randomly selected driver will receive a ticket next year? Okay, so this is your initial state matrix. 5% received a ticket, 95% did not receive a ticket. So if you take this initial state matrix and multiply it by this transition matrix P, you actually get 0.116 and 0.884 for the next state. So the probability that a randomly selected driver will receive a ticket next year, given that information, would be about 11.6%. And of course the probability that they don't receive a ticket is about 88.4%. And then if you go to the next year, you multiply that state matrix for that initial year times P again, multiply the new state matrix times P, and you get a little over 12%, so about 12.4% for the probability that they get a ticket the second year. So that's some pretty interesting stuff, huh? Now you probably see a pattern developing here. We start with the initial state matrix S naught, and to get S1 we do S naught P, and then to get S2 we do S1P. So S2 would be S naught P times P, which is S naught P squared. And then to get S3 we do S2P, but S2P is S naught P squared, so S3 is S naught P squared times P, which is S naught P cubed. So following this pattern, you can see that if you wanted any initial state, all you have to do is take S naught and multiply it by the power of the transition matrix to the power of the state you're looking for. So if we wanted S5, we would just take S naught, which is the 0.05, 0.95, and multiply it by this state matrix to the 5th power. And actually, you can use a matrix-capable calculator to compute that, but that's how you would calculate S5. And this leads us to a theorem that says if P is the transition matrix and S naught is the initial state matrix for Markov chain, then the kth state matrix, Sk, is S naught times P to the k. So just like up here, the 5th state matrix was S naught times P to the 5th power. So if I wanted to know the 4th state matrix here, then basically, let's say we wanted to go back to one of our examples. Let's say that our transition matrix is 0.1, 0.9, 0.6, 0.4, and our initial state matrix is 0.2, 0.8. So if I wanted to find S4, I would need to do S0 times p to the fourth. Now, you can do it a couple ways. The easiest way would be to just use a calculator and enter this matrix P and then tell it to raise the matrix to the fourth power. If you don't have a calculator handy, well, to get P to the fourth, what you can do is get P squared and then square it again to get P to the fourth. But the way you get P squared is you just multiply P times P. So we can just take this matrix and then multiply it by itself, and then we get this matrix, which is P squared. And then if we multiply P squared times P squared, so here P squared times P squared, then we get P to the fourth. Okay? And then finally, to finish it out, we have to multiply that by S0, so the initial state matrix. So now we take the initial state matrix, S0, and then we multiply it by P to the fourth, and then we get the fourth state matrix, which is about 0.3875 and 0.6125, so about a 39% and 61% chance. Okay, we're going to do one that involves a larger transition matrix. So let's say part-time students in a graduate program are considered entry-level students until they complete 15 credits. After that, they are considered advanced level and can take more advanced courses to prepare for graduation. Past records indicate that at the end of the year, 10% of the entry-level students, and we'll call those E, drop out of the program. And the program is D. And then 30% become advanced level students, so we'll call that A. That state we'll call A. And then also 10% of the advanced level students drop out of the program, and 40% of the graduate students each year. So students that graduate or drop out do not return. So let's draw a transition diagram and a transition matrix. So I've got four circles here. E is the entry-level students, A is the advanced level students, D means they drop out, and G means they graduate. Okay? So let's talk about the entry-level students. Now, on the entry-level students, it says 10% drop out. So 10% travel to this state. Okay? And if you read the problem, it says after that 30% go to the advanced level state. So if 10% drop out and 30% go to the advanced level state, that leaves 60% that return or remain as entry level. Now, as far as the advanced students, it tells us that 10% of those drop out. So we've got 10% dropping out, but we know that 40% of those graduate. So 40% graduate, and then so that means if 10% drop out and 40% graduate, that means that 50% remain in the program, so they return to the advanced level state. Now, what you don't have is you don't have anybody going from the advanced level to the entry level, and also you don't have anybody going from, once they drop out, they don't do anything else, so they continue to drop out. They continue to be dropped out at a 100% rate. So once they drop out, they don't return, so 100% of them remain dropped out. And then those that graduate, 100% of those stay graduated, so they don't go anywhere after they graduate. So this is a little bit confusing, but let's put it in a transition matrix. So those that go from entry level to entry level over here is 0.6. The probability going from entry level to dropout is 0.1 from here. The probability going from entry to advanced is 0.3 from here, and the probability of going from entry to graduate is 0, because you can't go from entry level to graduate, so that's 0. And then from dropout to entry level, 0. From dropout to dropout, that's 1. And again, you can't go from dropout to advanced level, so that's 0. And you can't go from dropout to graduate, so that's 0. Okay, you can't go from advanced level to entry level, so that's 0. 10% go from advanced level to dropout. 50% go from advanced level back to advanced level. And 40% go from advanced level to graduate. And then from graduate to entry level, 0. Graduate to dropout is 0. Graduate to advanced level is 0, and graduate to graduate is 100%, which is 1. Now the question here says draw a transition diagram and transition matrix, which I've done down here. And then it says what is the probability that an entry-level student graduates within 4 years? So we want to compute P4 so that we can get 4 years. Well, P to the 4th, I just took this matrix and I put it in a calculator and I raised it to the 4th power. And this was the result that I got. So now, if I want to know the probability that they went from entry level to graduate level in 4 years, this is the four-year state matrix. So look up entry to graduate, and that's right here. So about 36% entry level students graduate in 4 years. The other question says, what's the probability that entry-level student drops out within 4 years? Well, I do the same thing, except I go from entry-level to dropout, which would be right here. And so there's about a 31% of entry-level students that drop out within 4 years. And of course, you could answer several other questions, like what percent of students go from advanced level to drop out? What percent go from advanced level to advanced level? What percent go from advanced level to graduate in 4 years? So very interesting concept, these Markov chains. And we'll discuss them a little further in the next section.